There we go. Go resume recording. Okay, there we go. So for most folks, this is where the recording will sort of start here. Sorry. But so yeah, the vancomycin that binds calcium here in this, and vancomycin is also a biotech thing, right? It's derived from bacteria also. And we're just ripping off Mother Nature here, left and right. I love it. So it's a brave new world, I guess. But so when this uh, the blue emission and the yellow emission, when you have a biosensor like this, the emission intensities are typically mixed, right? Because you have some that's emitting in the blue and some emitting in the yellow here, and uh, and there's a variability in the yellow component as a function of potassium, right? And it's never actually zero, right? And then actually, as you get close to saturation, this will level off, right? So so in order to quantify this response, you need to be able to access the data spectrophotometrically. So you need at least two wavelengths, right? You need a 475 and a 525, right? Nanometer wavelength, right? And so we're going to try to make a little progress on how to do that here in the analysis of a mixture. So uh, here is a mixture analysis, right? Uh, if you have simply a mixture of two non-interacting things, just like, just two different things, right? X and Y. This could be, for example, toluene and acetone, and we're going to give that a try later on this semester, right? Uh, then the absorbance of the mixture will always be some function of the absorbance of X and the absorbance of Y, right? So at any wavelength you choose, you might see this dashed absorption spectrum, right? And this dashed absorption spectrum, at whatever wavelength you choose, it should be decomposable into the sum, or it should be the sum of some amount of X and some amount of Y, right? The absorption from some amount of X and the absorption from some amount of Y should add up to the absorption of some of that mixture, right? And so the way that we express that is simply AM equals AX, we'll say Y plus da da da, right? And if you substitute Beer's law in there, you get drunk, and then it looks all weird like this. AM equals X, A mixture equals AX, which is epsilon X BX, plus AY, which is epsilon BY, the concentration of Y. And so this encodes the total absorption in terms of some constants and the concentrations of X and Y. And normally what we want to do is we want to back out X and Y, because it's A is an accessible measurable, epsilons are knowable, and X and Y are, well, they're the they're the experimental variables normally that we're going after. So when you do this, it comes down to, X equations, X unknowns. And so we need to use as many wavelengths as we have unknowns, right? And for two components, we need two unknowns, right? And then, if, it's possible, for example, here, let's go back up here, right? And if we look at this spectrum, off to the right here, let's say it's 700 nanometers, and we were just to blow up this 700 nanometer piece, you would see that the extinction coefficient for the Y component is here. That extinction coefficient out of 700 is nearly 0, right? So the mixture and the X component have the same value here, right? So that tells you that whatever standard X you had here, you have that same concentration in the mixture. Does that make sense? That should make sense to you. Gianluca, does that make sense to you? Drink your coffee.
Yeah, it's still early, but yeah, it's starting to make a little sense.
Okay. So if X in this standard were 1 millimolar, what would X in this mixture be? I'm trying to sound mean, and I'm always afraid that I'm going to actually succeed. And as I get older and crotchetier, I get closer to success. So I'm going to have to tone myself down a little bit, I think. So Gianluca, that's a question directly for you. Da, 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 da. Da, 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 da. Okay. Gianluca, would you like me to restate the question? Can anybody hear me?
I
Yes,
hear you.
I hear you.
I think Gianluca is taking a much needed break.
Went to get a second cup of coffee.
I think so. I think so. Okay. So, who else would like to try this game? Maybe Taryn, would you like to try? Oh my God. Mina?
What was the question again?
Excellent question. The and the way you say that is, Alex, could you restate the question? Because I'm the Jeopardy host, Alex Trebek. Even though poor guy's dead. Died of pancreatic cancer. So the question is, in this mixture here depicted by the sum of X and Y, there's obviously some X and some Y, right? Now, if in this Y component, there is 1 millimolar of Y, in this Y, pure Y standard here, this green line, then how much Y is in the X plus Y spectrum here?
Is it the same?
And why on earth would you say that?
I'm not sure.
Okay. Well, that's a very good start. Solomon, since you want to get an A, tell me why.
Oh, so yeah.
Yes.
Okay.
Yes, Mina?
Now for a second I thought I got it, but
Oh, okay. All right. Okay. So let me state it again. The concentration of Y in this standard, the solid green line here, is 1 millimolar, right? Then you add some X, right? Oh wait, no, sorry. The mixture of X and Y is given by this dashed line here. And the mixture of X and Y is higher than either of the standards at any wavelength here, pretty much, except out here, right? And out here, it overlaps exactly with the oh, holy fuck. I was asking my question wrong. No wonder no one can answer it. Everyone gets an A. So I think I was asking for Y. I think what I want to do is I want to ask for X. What is the concentration of X? If the standard X is 1 millimolar, what is the concentration of X in the combination of X and Y here?
Are you sure you're asking the question correctly?
Is that Gianluca? That is a good try, but yes, I'm answering it. I'm asking it correctly right now. I must be. I
mean, we still have the same amount of X, but since we've added Y, we've diluted everything.
Okay.
So the concentration's not the same anymore.
Don't think about it that way.
Okay.
Don't think about it that way. Just think about 3 separate solutions: a standard of X, a standard of Y, and a mixture of X and Y. Right? And this X standard is 1 millimolar.
Okay.
1 millimolar, right? And I say, okay, here's the spectrum of X and Y. What is the concentration of X in the mixture of X and Y?
Shouldn't it still be 1 millimolar?
All right, I accept that, but why? That's my.
I guess we haven't added any of the X analyte or taken any away, so the X itself is the same. It's still bothering me that our total volume has changed, though, because we have added something.
Okay, so there's no. Don't think of this as adding anything to anything else.
Okay.
Think of this. These are millimolar solutions in water, let's say, right? So you got this by making solid Y plus water, solid X plus water, solid X plus solid Y plus water. There are 3 separately prepared solutions. Okay, Cindy?
Okay.
So it's like you made lemon Kool-Aid for the boys, raspberry Kool-Aid for the girls, and then there's not a third gender. Oh well. So and then for the adults, you took raspberry and lemon and you put them both in to make Kool-Aid for the adults. You mix them together with the Kool-Aid, and the water, right? So you got 3 separate spectra here, right? Independent. So now, if this X spectrum contains 1 millimolar of X, how much X is in the X plus Y? Just by inspection here. Kareem got it correct. He said 1 millimolar because that's the only possible answer that it could be, given what I've set up. But my question is why?
Is it because the absorbances add up? So like X's absorbance plus Y's absorbance adds up to the absorbance of X and Y.
True. But how?
Yeah, I was going to say just by looking at the graph, you can kind of infer that like the amount of absorbance added in the mixture combo is just the addition of X and Y.
Right. That's true. Now you guys are applying your multivariate minds to this wonderfully, I might add, wonderfully, amazingly. But I want you to dumb it down just a little bit for me. Right? And I want you and Brandon to look at this graph in this region. I'm going to try to explode this up just a little bit. Geez, this couldn't possibly hurt, could it? So if we look in this region, what can we say about the absorbance spectrum of the standard, the 1 millimolar standard X, and the mixture X plus Y, looking at it in this region only?
If you look at the thing around that 700 mark, they'll be equal.
Right, exactly. The 1 millimolar standard X and the sum X plus Y have the same absorbance. Now, how is that possible? Casey?
It's too early.
It's too early. I know it's too early. Come on, somebody else help me out here.
Is it at some wavelength the absorbance of the X is almost the same as absorbance of X and Y mixture?
Exactly correct. And the concentration of X is 1 millimolar. And I'm asking what the concentration of X is in the mixture X plus Y. Right? And the answer has come out, it's 1 millimolar. Yeah, that's totally true. And my question again is why? And you guys are coming
Is it
up
because
on that
X is
answer.
the predominant species?
It is not the predominant species, right?
Okay.
Because if you look at this dashed line, it's got X and Y pretty much everywhere. And they're, I don't know, maybe it's predominant, but like, I don't really think so.
Is it at 1 millimole the Y have not absorption? So just the X absorption, and then that's why the X only show up on the absorbance line.
Van, you take home the prize. Now, can you convince Kareem of the same thing you just told me? That is your goal. So Van said that the absorption of Y at 700 nanometers is 0. Therefore, any absorption you see in the mixture is going to be due to X. Therefore, if the absorption of X and the absorption of the mixture are the same, then the concentration of X in the standard and the concentration of X in the mixture must be the, finish my sentence. Last word.
The absorbance of the X only.
There's one word I'm looking for here.
The mix, it will match together. It
They
will
won't match. They'll
no.
be the same. Yes.
The absorbance of X and Y will be the absorbance of X.
Yes. And the concentration of X in the standard will be the concentration of X in
Y.
No, in X plus Y. I tricked.
Wait, so if the absorption of X, so if you're not seeing Y at all, then why wouldn't the absorption of both be the same as X?
What?
So you're saying that we're not actually detecting Y, right?
Well, at 700 nanometers, way out here at this edge here, right?
Oh, but you are at the lower wavelengths.
Right. At the lower wavelength,
Oh, okay.
there's it's like there's this plus this equals this, right? You know, this is a stupid example, right? Because in this example, I think the X plus Y always adds up to be X plus Y here, right? So the concentration of X in the standard is equal to concentration of X in the mixture. Concentration of Y in the standard is equal to concentration of Y in the mixture. Yes? Okie dokie. Does that make sense? Okay. Are we going to move on now? Okie dokie. Okay. Okay. So, you know, where there's, you know, at this wavelength out here, at this, you know, there's relatively little absorption due to a single component, right? Like only X, only X absorbs out here. So you can measure X directly just with a single absorption measurement at 700 nanometers, right? You know, does that make sense, Casey?
Yes.
Good, okay. Now, if you measure, now if they both absorbed out here, right, then you'd be in a little bit more difficult area, right? But so long as there's some difference, right, some shape to this mass, then you can untangle it. Then you can untangle it, right? It's so long as you have absorptions at two wavelengths where the extinction coefficients are different, right, for the two components, then you can sort it out. Because you have like A at lambda 1 and A at lambda 2. And let's get the equations for that, right? It's like there's, if you just choose two wavelengths here, right? 447 and 612, right? Then at 447, you've got epsilon prime X and epsilon prime Y, right? This is just the extinctions of X and Y at that wavelength, at this 447, right? And so the absorbance of the mixture will be epsilon BX plus epsilon BY, right? Or epsilon X BX, epsilon Y BY, right? And because we're specifying wavelength here, let's give it a prime, right? We have to label it something. So we're going to say A prime is equal to epsilon X prime BX plus epsilon Y prime BY, right? That's just the sum of the absorbances of X and Y at this wavelength will equal the total absorbance. Do you guys believe that? Do you believe?
Yes, I believe.
Folk, you're always the first. Come on. We have to get the skeptics in the audience.
That makes sense. I get it.
There you go. We even have a sort of a rationalist on our side now. Kareem, do you believe?
Yeah, Dr. Terrell, whatever you preach, I'll believe.
I love it. I'm looking at your picture up there. That's why I'm sort of facing away. But yeah, so it's just saying that the absorbances add up at 447. The absorbances add up at 612 too, right? So let's say at 447, if X and Y are both 1 millimolar, which has the higher extinction coefficient? A equals epsilon B, right? Epsilon BC, right? And if X and Y are the same concentrations here in these two standards, which has the higher extinction at 447, X or Y?
It has to be X because X has higher absorbance.
Exactly. Now, if we go out here, which has higher extinction, X or Y?
Y.
Right, exactly. Good. So now, so this means you have two equations and two unknowns. The unknowns are X and Y, right? If you know epsilon X and epsilon Y, you get them from the standards, right? Then you know A prime and A double prime, you can get X and Y, right? So let me ask you this. Is X in this first equation different from X in this second equation?
No.
Does anybody believe Cindy?
Yes, I believe in her.
I believe.
Thank you,
I
Ben.
also.
Yay!
Oh, I have friends.
Yay! 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 Nicholas, what do you think of these children?
You're correct.
They're correct. They are correct. Exactly. So X and Y in the two equations is the same thing. This is the concentrations in this mixture, right? Good, good. So there we go. So now there's ways to solve this shit. And I do not like Harris's approach here. He just jumps right into determinants, does not even show you why. Then he's got all this blah, 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 you know. And honestly, I don't understand it. I don't understand why. It's a bunch of nonsense here.
Why are we doing determinants, Dr. Terrell?
No, I don't know. I don't know. It sucks. I mean, what I do in this case, right? Okay, let me let's try this test yourself thingy. And I'll write down the values here. A at 272 equals 0.7, and absorbance at 327. Oh, what? 327. Whoa. Is 0.550. So, and we have this information, right? We have epsilon for X and epsilon for Y, right? It's 16.4. And 39.90. And then Y is 38.70. And X is 64.20. So here, let me. So let me switch on over here to the document camera. Okay. So sorry, this is a little bit, I may need to refocus this a little bit, but there we go. But this is the data that we have. At 272, we have an absorbance of 0.7 and 2 extinctions. At 327, absorbance and 2 extinctions, right? So the actual equations are A, 272 is equal to epsilon C, epsilon x cx, and we'll call this prime, right? Because this is the 272, and epsilon prime y, cy prime, right? That's a double prime oops, there's no prime on the x, and epsilon y double prime cy. There's no prime on the y, right? The cx and cy are simply what they are, right? They don't depend on where you measure it or anything, right? So let's just put in the numbers. So let's make this easy, right? We got 0.7 is equal to epsilon x, which is 16,400 cx plus 3870 cy, right? And then 0.55 is equal to 3990 cx plus 6420 cy, right? And there's a variety of ways to solve this, right? You can solve it directly with matrix math, and you can also break it down algebraically and solve it. But y'all would agree, right, that these two equations, there's probably a solution for cx and cy, right? Yes.
I think there definitely is a solution.
Yeah, there's definitely a solution, right? Otherwise, why the hell would I be, employed at this university and wasting everyone's time? So, so this is how I would do this. I'd break it down into two equations and two unknowns, right? And then basically you can solve for cx in this equation, right? And then shove that into here. That'll be one equation only in cy, and you can solve for cy, right? And then substitute cy back and solve for cx. There's a variety of ways to do that. Now, and you can, I'm sure you can do it this way. I don't really quite follow what they're doing here, So, so we can do this later, right? Yeah, so why don't we do this? Why don't we do this in Excel, right? I'm sort of getting lazy, computery lazy here. So I'll go ahead and bring up Excel and we can do this in Excel.
Would you normally let us use Excel on like an exam if we had something like this, or?
Yeah.
Because by hand it would take a while. So
yeah,
as I'm sure, that's the reason I'm sure you're not doing.
Yeah, exactly. I really, I feel like algebra was designed to torture youngsters. And, I'm too old for that shit, frankly. So let me change my share here. And let's put in the values here. 0.7. Come on. 0.55. Now this is 16,400, 3870, and 3990, and 6420. Right, and actually, why don't we put it like this, right? This is the absorbances, right? And they're going to equal the extinctions times the concentrations. If we'll make a little concentration matrix, right? This would be Cx and Cy, right? And so what we would say in matrix math is that A equals epsilon C, right? And you notice I'm dropping the b values here, right? I'm just saying let's just assume they're 1 and just humor me for right now, right? If we do everything in unit length cuvettes, then we're good here, right? And so this works, right? Because Cx and Cy, when you multiply them, the matrices here, then you lay this matrix on its side and you multiply Cx by this and Cy by this and Cx by this and Cy by this, right? And so that works, right? So so let's call this capital A. Oops. Capital A is equal to capital or epsilon, right? Times C, right? And therefore, if there's an inverse to epsilon, right? Oops. Right, then we can say that A, oops, what the hell? A times eps minus 1 equals will equal C, right? I think, or it could be epsilon minus 1 times A. I'm not exactly sure. But let's see if we can invert this matrix, right? So oops, if we can invert this matrix here, then we should be good. Right? Yay! It came out okay. It came out okay, right? So now let's take put this guy down here. And then what we're going to do is we're going to I'll make a 2x2 matrix here. And I'm going to say this is going to equal the multiplication of, I think it's like this, and then comma this. And if it comes out funky, I'll reverse it. Right, there we go. That's the answer. 26 and 69 micromolar, right? So this is going to be Cx and Cy. Right?
I got that by hand about 5 minutes ago.
Oh, come on. Come on. Oh my
okay,
God.
so it's like you were explaining your setup. Okay.
Okay. Oh, man.
Wait,
And
did you
also,
end
I'm
up doing
sure-
matrix math then?
I did.
That-
I did. Yeah.
Oh, okay.
See, this
But he
is
just
the-
put it into
this is
Excel
the
instead.
inverse of this matrix here, right? And so this is the product of this matrix and this matrix. Right? And so this comes out. And so so let me just check this, right? Let's check the math here. And let's say that let's just say that let's try to reproduce A1. So or this 0.7 value, right? This should equal Cx times epsilon x plus cy times epsilon y. Oh my God, it came out to exactly 0.7, right? That's good. And this should be equal to cx times this guy plus cy times this guy. This should come out to 0.55, right? Great. Love it. So this one worked out pretty neatly. Thank goodness.
So, Professor,
Mhm.
can we, like, for an exam or something like that, when if you ask this question, can we just either do it by hand or just do it in Excel?
Yeah, I don't think that you will definitely have access to Excel. Let me state that out up front. That there's no, I don't care how you accomplish the answer here. I think that's totally fine if you use Excel. I'm not certain that I'm going to give you this exact type of problem on an exam, but it will definitely be in the homework. So, and actually the homework is posted now, so you guys should have access to homework on this subject. So in any case, so this works out, right?
Okay.
Yeah, let me take a peek ahead and see what we've got coming up here. There we go. So this is how we solve this one, right? And, you know, it came out to these guys. That's fine. And then, oh, and one important thing is Control-Shift-Enter. You know, or Control-Shift-Return, whatever, same thing on the Macs, you know. And the idea is you highlight the two cells where you want it and you say Control-Shift-Enter, you know. Highlight the two cells, type in the equation and type Control-Shift-Enter. It's an idiosyncrasy of Excel. Right? So, so what we typically do then is we use this is an exact, well, no, this is no more exact than the data that you use, right? And since there's always uncertainty in data, it's normally better to use more data, right? Because if there's like a little bit of fluctuation in the data, you want to average over the fluctuations. And so, let's see here. So here's an example, right, where you actually have, you could have a mixture of paraxylene and dichloroethane, right? You know, and then when you add up that mixture, you'll get, you know, a larger absorption that has both bands in them, right? I don't know. This is one way to do it. And you can decompose that into a series of wavelengths and a series of absorbance of standards, and then a series of absorbance of the mixture, right? And in order to decompose all that, the proper way to do it is to use least squares, right? And the idea is that you'll have a calculated value, you'll have a calculated absorbance at each wavelength, right? You'll have a calculated absorbance that will equal epsilon b times your gas concentration for X plus epsilon B plus times your gas concentration for Y plus epsilon B times your gas concentration for Z, right? These epsilons, epsilon X, X, epsilon Y, Y, epsilon Z, Z. And, basically this is just a restatement of the hypothesis, the good hypothesis that A of the mixture is equal to the sum of the components, right? So what you can do here is you can use linest. Well, I mean, you can do both ways. You can use a 3x3 matrix, right? Or you can use linest. And what linest is going to do is it's going to minimize the squared sum of the residuals, right? So let's just talk about what a residual is. And let me do this graphically for a moment, and then we can go back and do it more analytically. Oh, darn it, where are you? There we go. So so let's say that we have a spectrum which looks like this. Then we've got a standard that looks like that, and a standard that looks like that. This is our mixture. This is our let's say it's our pure A, and this is our pure B. Right? And what if we have these spectra, they're going to consist of a bunch of points, right? And in theory, we could just take these three values and these three values, right? And we can, say A for the mixture is equal to epsilon, which is going to be 2 by 2, times C, right? Which will be 2 by 2, right? This is going to be CX, CY. This will be A1, A2, and this will be, epsilon 1X, epsilon 1Y, epsilon 2X, epsilon 2Y, right? And you can solve this way, right? And this will give you, if you can invert epsilon, right? This will give you CX and CY, right? But this is not the way this is typically done. What is typically done is least squares. So in least squares, what you're going to do is you're going to have a mixture, an experimental mixture, right? This is what you measure, right? And then you're going to have a mixture, a spectrum that you simulate, right? And the simulated mixture is just going to be equal to epsilon x c x plus epsilon y cy, right? And this will be just the absorbance that you measured, right? And then you'll have this at a whole bunch of different wavelengths, right? And what you're going to do then is you're going to measure, you're going to take the difference between these two guys and you're going to square it and you're going to add it up. Then what you do, then you allow Cx and Cy to float as to vary. And then you minimize the sum. And let's call the sum, let's give the sum a name. Each value will be chi. Well, no. Let's just call the sum chi squared, right? Okay. And then, and this process of minimizing the sum chi squared, you do it algebraically. I mean, you don't actually do any of this. You let the friggin' computer do it. It's super easy. I mean, all you got to know is what's X and what's Y, and boom, the problem is solved, And, but once you get this done, it's basically minimizing the partial of X, or chi squared, with respect to Cx, and partial of chi squared with respect to Cy. It does this simultaneously. And, as long as you have enough data points, it works. So let's see here. So let's just take maybe 5 minutes and then I will shut the hell up. I promise. We can get on with our morning, have our coffee. Yay! Play our guitars, Casey. No, you can't play the guitar. Sorry. I know you can't play the guitar. And then, but let's just sort of ask ourselves what the hell is going on here, right? Let's go back to this, right? If we're minimizing chi squared, what we're doing is we're adding up the sum of the squares. Like this is r sub, 1, r sub 13, right? And this is r sub 5. There's r sub 1, right? And if we add up the r values squared, this is what chi squared is. Does that work? So now when our guess for Cx and Cy, when this matrix is optimum, right? When those two values are as close as they can get to the truth, right? Then chi squared will be a minimum. Provided all of our assumptions are correct. The assumption that, A1 is equal to epsilon times, epsilon times x plus epsilon times y, that summing still works, all that, right? So now if our estimates of the this is probably not like a perfect way to depict this, right? Let me use a new piece of paper, and let's just let's move forward here. Let's say that we have a all right, let's say we've got something like this, right? And in this case, we measure chi squared, and it's large. And then we adjust Cx and Cy, and we make them both larger. We adjust them up, right? And the new value we have new Cx and Cy values, right? And then we measure chi-squared. And what will the value of chi-squared be now versus before, right? And so we've got is this is the first case. And this is the second case, right? This is R1.
Can you move the paper up a little bit?
Of course I can, yes.
Thank you.
Ay Dios. So the question I want you to answer for me is, what is the functional form of chi-squared versus our guess for C sub x? So chi-squared, and let's say that this third guess is optimal, right? So when the guess is optimal, chi-squared will be what?
A minimum.
Minimum.
Mm-hmm. Yes. Casey, do you see?
I'm still copying down the notes.
These fast note takers. I hate them. I'm just kidding. I got a ticket once, and I was talking to my friend, and she said, "Oh, those darn cops." It was like such a gentle way of chastising the cops. I just felt like so disarmed. Like, he's just doing his job, man. So you fast note takers, you're just doing your jobs. So, good morning, Pauline. Good morning. Good morning. Good morning. So, so chi-squared will be, so stop taking notes now, Casey. Answer me this. If you look at the screen here on my pen, right, there's our first guess. There's our second. There's our third guess, which goes right through the points. And there's our fourth guess, which goes above the points, right? The chi-squared is the sum of the squares of the distances. There's chi1, chi2, chi3, etc. Then there's chi1, chi2, chi3 for the second gas, and chi1, chi2, chi3 for the third gas. Yeah. I'm sorry, the fourth gas, right? Now, let's just say that the first gas is here. That's the sum of these lines here. What will the sum of these second lines be relative to this value up here? Let's say that's 0 and this is, some 1 or 1, 1,000 or a million or whatever up here. Our second guess here,
It'll be lower.
it'll be lower, right? And our third guess will be
0.
it'll be lower still.
Okay.
And our fourth guess will be
Are you going based off of your little diagram?
yes.
It'll be lower.
So remember that we're adding the squares of these guys. So they're all
So it'll be
positive.
higher.
It'll be higher again, right?
Okay.
And in fact, this is a parabola. And this guy in CX and CY is a parabola of revolution. And I've officially kept you guys 3 minutes over. So I'm going to leave it here and then we'll pick it up next time and we'll talk a little bit more about it. All right. I assigned homework due a week from Friday on this chapter. It's 19 problems, I think, or it's like 16 or something. I took out a bunch of the nastier ones.
Thank you.
You're welcome. All right,
Unless
guys.
it's something we really need to know.
Exactly. I try to take out the nasty bits. Okay, guys. Thank you so much. I love you guys very much. Have a good day. Have a good life. And I will see you on Thursday, if not shorter.
Thank you, Dr. T.
Thank you, Dr.
Bye,
T.
Brooke. Bye.
Thanks,
Thank
Dr.
you.
Terrell. Have a good life.
Thank you.
Thank you. I knew I was going to get called on that.